4 minutes ago, buried inside decades of data from humanity's most distant machine, scientists confirmed something that sounds almost impossible to say out loud. At the very edge of our solar system, where the sun's influence finally gives way to the emptiness of interstellar space, Voyager 1 flew directly through a wall of superheated plasma, hotter than the surface of the sun itself. And somehow, that wall didn't destroy the spacecraft, didn't disrupt its instruments, and left behind a magnetic signature that nobody expected to find at all. Stick around, because this is one of the strangest confirmed findings to ever come out of the Voyager mission, and by the end of this video, you'll understand exactly why. Scientists are calling it a genuine surprise, decades in the making. Let's rebuild the picture from the beginning. Voyager 1 launched in September of 1977, sent out on a mission originally designed to last just 5 years, flying past Jupiter and Saturn to capture the first detailed images of those giant worlds. It succeeded, spectacularly, discovering active volcanoes on Jupiter's moon, Io, and a thick, hazy atmosphere wrapped around Saturn's moon, Titan. But once that primary mission ended, Voyager 1 simply kept flying outward, carried by momentum alone, drifting farther from the sun with every passing year. In August of 2012, Voyager 1 crossed a threshold no human-made object had ever crossed before. It passed through the Heliopause, the outer boundary where the constant outward pressure of our sun's solar wind finally loses its battle against the pressure pushing inward from interstellar space. Crossing that boundary made Voyager 1 the first spacecraft in history to officially leave the solar system and enter true interstellar space. If you're new to this channel, we dig into discoveries exactly like this one every single week. So make sure you're subscribed before we continue, because this story only gets stranger from here. Scientists expected that once Voyager 1 crossed into interstellar space, conditions would settle into something colder, calmer, and more predictable than the turbulent environment near the sun. Instead, the data coming back told a very different story. Right at that boundary, Voyager 1's instruments detected an extraordinarily hot layer of plasma, with temperatures reaching hundreds of thousands of degrees, dramatically hotter than the surface of our own sun. Researchers began referring to this superheated boundary layer using a nickname that stuck immediately. They called it a wall of fire. Now, before your mind jumps to something out of a science fiction movie, it's worth understanding exactly what that phrase actually means in this context, because it's genuinely fascinating on its own. This wall of fire isn't fire in any traditional sense. There's no combustion, no flame, nothing burning in the way we experience heat and fire here on Earth. Interstellar plasma at this boundary is so incredibly thin, so sparse, containing so few particles packed into such an enormous volume of space that despite registering temperatures in the hundreds of thousands of degrees, it wouldn't feel hot at all. There simply aren't enough particles present to transfer that thermal energy the way a fire or a hot surface would here on Earth. Voyager 1 flew directly through it, and its instruments barely noticed any physical stress at all. What actually stunned scientists wasn't just the extreme temperature itself, it was what that temperature revealed about the boundary's structure. This superheated layer forms because particles from the interstellar medium collide with the outer edge of our sun's magnetic bubble, the heliosphere, and get slowed down and heated dramatically in the process, similar to the way air heats up when compressed rapidly. Researchers had long suspected something like this boundary layer might exist in theory. Actually flying a spacecraft directly through it and confirming those extreme temperatures with real instrument readings was something else entirely. But the true surprise came from a completely different measurement, one nobody had specifically predicted. When researchers analyzed the direction and structure of the magnetic field within this superheated boundary layer, they found that it aligned remarkably closely with the magnetic field, found deep inside the heliosphere, well within our sun's own protective bubble. In simpler terms, the magnetic field just beyond the edge of our solar system appeared to be connected to, or at least strongly influenced by, the magnetic field coming from our own sun far further out than anyone expected that influence to reach. If discoveries like this one, real data pulled from the literal edge of our solar system, get you as fascinated as they get me, do me a quick favor and hit that like button. It genuinely helps this channel keep making videos exactly like this one. This finding matters more than it might initially seem because it directly challenges some of the basic assumptions scientists have long held about where our sun's influence truly ends. For decades, the Heliopause was treated almost like a hard boundary line, a clean division between the space belonging to our sun and the space belonging to the wider galaxy. Voyager 1's data suggests the reality is far messier and more interconnected than that clean boundary implied. The sun's magnetic fingerprints appear to stretch further into interstellar space than previous models accounted for, blending and interacting with the surrounding galactic environment in ways that are still not fully understood. Researchers studying this discovery have been careful and measured in how they describe it. precisely because they know how significant it could turn out to be, if confirmed and expanded upon by future observations. This magnetically aligned wall of fire could reshape how scientists model the entire boundary region of our solar system, changing not just theoretical understanding, but also the design of future spacecraft meant to study this exact region in far greater detail. And that future is already being planned. NASA and other space agencies have discussed concepts for dedicated interstellar probe missions, spacecraft specifically, designed and equipped from the very beginning to study this boundary region with instruments far more advanced than anything available on a machine built back in the 1970s. Voyager 1 was never meant to make this discovery. Its instruments, decades old, running on technology that predates most modern computing entirely, simply happened to be in the right place at the right time, stumbling into one of the most important boundary discoveries in the mission's entire history almost by accident. That's part of what makes this story so remarkable when you really sit with it. Nobody designed Voyager 1 to study a superheated, magnetically aligned wall of plasma at the edge of interstellar space, because nobody fully understood that such a structure existed until the spacecraft actually flew through it and sent the data home. Every instrument still working on Voyager 1 today, the magnetometer and the plasma wave subsystem, both of which remain active as of this year, continues quietly gathering information about an environment that keeps revealing new surprises decades after anyone expected this aging machine to still be capable of teaching us anything new at all. There's real urgency behind continuing this work too. Voyager 1's power supply keeps declining year after year, forcing engineers to make increasingly difficult decisions about which instruments to keep running and which ones to permanently shut down. Just this year, engineers powered down the Low Energy Charge Particle instrument, one of the tools that had helped researchers understand cosmic rays and precisely determine when Voyager 1 first crossed into interstellar space back in 2012. NASA engineers have been testing a new power management approach on Voyager 2 first, hoping that if it succeeds, they can attempt the same fix on Voyager 1 and potentially bring a silenced instrument back online, buying just a little more time to study this strange boundary region before the spacecraft's power finally runs too low to continue operating at all. Every additional month, Voyager 1 survives, adds more data to an already extraordinary dataset, one that keeps forcing scientists to reconsider exactly where our solar system truly ends and where the wider galaxy genuinely begins. The Wall of Fire discovery is a perfect example of why that continued operation matters so much. It wasn't something scientists were actively searching for. It was something Voyager 1 simply flew directly into, and in doing so revealed a layer of complexity at the edge of our solar system that nobody had fully appreciated before. Researchers are now combing back through years of additional Voyager data, looking for other overlooked signatures that might have been hiding in plain sight this entire time, patterns that didn't seem significant until this new understanding of the boundary region gave scientists a fresh lens to re-examine everything through. It's entirely possible that other unexplained anomalies recorded over the mission's decades-long history in interstellar space might finally start making sense in light of this discovery, or might raise even more questions than they answer. There's a deeper reason this discovery unsettled so many researchers when it first came together, and it has to do with how physics usually behaves at boundaries like this one. In most models, scientists build a transition zone between two very different environments tends to smooth out gradually, one condition slowly fading into the next over some measurable distance. What Voyager 1 found instead looked far sharper and far more structured than that smooth transition model predicted, almost like hitting a genuine wall rather than drifting through a gentle gradient. That structure is part of why the nickname stuck so easily among the scientists analyzing the data. It behaved less like an edge fading into empty space and more like an actual boundary with its own internal shape and character. It's also worth understanding just how difficult it is to even detect something like this from so far away. Voyager 1's instruments were never built with cutting-edge sensitivity by modern standards. Its magnetometer and plasma sensors use technology that predates almost every piece of equipment found in a modern physics laboratory today. And yet, because the spacecraft was physically present, sitting directly inside the environment being measured rather than observing it indirectly through a telescope from millions of miles away, even relatively simple instruments were capable of capturing an extraordinarily rich picture of what this boundary region actually looks like. There is simply no substitute for being there in person, even when the instruments doing the measuring are decades behind modern technology. This is part of why scientists have pushed so hard to keep the last two working instruments on Voyager 1 alive for as long as possible. The magnetometer and plasma wave subsystem aren't just legacy pieces of equipment being kept on for sentimental reasons. They are, right now, the only instruments humanity has ever had, sitting physically inside this exact region of space, continuing to record data about a wall of fire that no other spacecraft has ever flown through, and none currently in development will reach for many years, if not decades. That reality adds real weight to every additional month of operation NASA engineers manage to squeeze out of this aging spacecraft. Every year, its nuclear power source loses a little more capacity, forcing harder choices about which systems stay on and which get sacrificed simply to keep the spacecraft transmitting at all. Engineers have described this process almost like carefully rationing the last bit of fuel in a tank that can never be refilled, trying to stretch every remaining watt of power across the instruments most likely to keep producing meaningful scientific data. What makes the wall of fire discovery especially significant in that context is that it wasn't found using some brand new instrument or some clever new analysis technique developed specifically to search for it. It emerged from data that had, in some form, already been available for years, re-examined and reinterpreted as scientists slowly built a clearer picture of what was actually happening at this boundary. That raises a genuinely exciting possibility for researchers combing through Voyager's archives today. If a discovery this significant was sitting partially hidden in existing data, waiting for the right analytical approach to reveal it clearly, there may be other equally important patterns still buried in decades of transmissions, waiting for someone to notice them. Some researchers have already begun revisiting older anomalies recorded earlier in the mission, wondering whether they might connect to this newly understood boundary layer in ways nobody previously considered. Details that once seemed like minor inconsistencies or measurement noise are now being re-examined with fresh eyes, in light of a discovery that fundamentally changed how scientists think about where our solar system's influence truly ends. It's a reminder that in a mission spanning nearly 5 decades, sometimes the most important discoveries aren't made the moment data arrives on Earth, but years or even decades later, once enough context finally exists to understand what that data was actually showing all along. None of this would even be possible without the sheer stubbornness of a machine that was only ever designed to last 5 years, somehow still transmitting nearly half a century later, still teaching scientists things nobody thought to ask about when it first launched. That's the quiet, remarkable core of this entire story, buried beneath the technical details of plasma temperatures and magnetic alignment. A spacecraft built before most of its current operators were even born just rewrote part of what we understood about the edge of our own solar system. If a nearly 50-year-old spacecraft using instruments built with 1970s technology can still stumble into a discovery this significant, purely by continuing to fly and continuing to listen, what else might be sitting quietly in decades of collected data, waiting for the right insight to finally reveal exactly what it means? Drop your thoughts in the comments and let me know whether you think this wall of fire is simply the last echo of our sun's reach, or evidence of something far more complex happening at the true edge of our solar system. If this story pulled you in the way it pulled me in while researching it, hit that like button. It genuinely helps this channel keep telling stories like this one. And subscribe if you haven't already, because Voyager 1 is nowhere near done surprising us, and when the next discovery comes in, we'll be covering it right here. 15 billion miles from home, a machine built before most of us were born flew straight through fire that couldn't burn it, and came out the other side, carrying a mystery scientists are still only beginning to understand.